Okay, test 3, computational problem 1. Two rectangular slabs of material, dielectric constants kappa 1 and kappa 2 are L meters wide, L meters long, and L over 2 meters thick. They're squeezed next to one another to create a block, L times L times L. A metal plate is put on two sides of the block as shown as figure A. The resultant capacitor is hooked up to a battery of voltage V. The block is then removed, rotated 90 degrees, and replaced between the two plates as shown in figure B. What is the ratio of the final capacitance to the initial capacitance? If kappa 1 and kappa 2 are each equal to 1, does the result make sense? Why or why not? Okay, so this is what we have. We have a metal piece of metal, and then we have a block with kappa 1 and a block with kappa 2, and then we have another piece of metal. Okay, and that's a metal plate, and that's a metal plate. Okay, then I'm going to go ahead and draw out, this is part A. Oh yeah, this is A. Okay, so now we're going to look at configuration B. Configuration B is this exact same thing, except we have kappa 1 and kappa 2 are like that. In both of these cases, this block is L by L by L in the third dimension. Okay, so, and that's true in both of these cases. Okay, you were given these homework problems, this exact homework problem. One of these is problem number 59, one of them is problem number 60. You guys all got these problems 100% correct. No one had a problem with these problems. With, maybe a little algebra here and there. There were a couple little algebra mistakes, but conceptually you understood what was going on. You understood that here, what do we have? We have two capacitors that are in series. What happens with capacitors in series? They add like this. And this is our total capacitance. Then you look at this and say, oh, look at this. This is just like two capacitors in parallel. This is not a surprise to you guys, as I said, because you had this problem. You had this problem in the chapter. You were given this problem, and you all got it 100% right. So, what do we know about the capacitance in parallel? We know the capacitors in parallel add. I'll do it like this: C1 plus C2. So. That's what we know. Now all we need to do is just figure out what these capacitances are. Well, once again, right on the equation sheet, kappa epsilon 0 A over D is the capacitance. So it's just a matter of figuring out what the A over D is and what the appropriate kappa is. So here, I'm going to go ahead, let's call this CA and CB. All right, just to separate it from 1 and 2. Well, you know what? I take it back. I'm going to change my mind. I'm going to call those C1 and C2. C1 and C2, since I've already done that over here. So, what is the area of C1? Well, it's L by L, right? So, my area is just L squared. So, I have kappa 1 epsilon 0 L squared. What's my D? It is L over 2. It's just half this distance here. L over 2. So what is that? That just equals 2 kappa 1 epsilon 0 L, and we're done. Okay? Now, what is C2? Well, C2 is exactly the same as that, except just with kappa 2 instead of a kappa 1. All the rest of the geometry is the same. So now we're just left with this. We are now left with 1 over 2 kappa 1 epsilon 0 L plus 1 over 2 kappa 2 epsilon 0 L, and then we're going to take the inverse of that. Well, in order to add those things, I'm just going to do this. Okay, in order to add those things, we just need to make certain we have the same denominator. In order to have the same denominator, the only thing we need is we need to multiply this one by kappa 2 over kappa 2. I'm just going to squeeze it in here. and this one by kappa 1 over kappa 1. Oops, you guys maybe can't see that. I just remembered that. I'll pull it here just so you can take a look at that. Okay, so kappa 2 over 2 kappa 1 epsilon 0 L kappa 2 plus kappa 1 over 2 kappa 2 epsilon 0 L kappa 1. So now we have the same denominators. Now we can add those because they are the same denominators. Okay, and then we can take the inverse when we add it. So we're going to have this. We have 2 kappa 1 kappa 2 epsilon 0 L over kappa 1 plus kappa 2. This is equals C. I'll go ahead and call this CS for C series. So our series capacitance is that. Okay, now we're just going to do this C1 plus C2 over here. Once again, all we have to worry about is kappa epsilon 0 A over D. That's the capacitance of each one of these. Well, what is it? Well, this time, the area here, it's L in one dimension, but it's only L over 2 in the other dimension. So our area is going to be equal to, I'm just going to write it like this. It's going to be equal to L squared over 2. Kappa 1, I'll do it for this top capacitor first. Kappa 1, epsilon 0, A is L squared over 2, divided by D. What's D? D is just L. So what does this equal? It equals kappa 1 epsilon 0 L over 2. And I hope everyone can see that our C2 is just going to be, in other words, the C for this kappa 2 is just going to be this exact same thing, but with kappa 2. And these are in parallel. How do capacitances add in parallel? They just add straight up. So our total capacitance in parallel is kappa 1 epsilon 0 L over 2 plus kappa 2 epsilon 0 L over 2. And I'm going to make this a little bit more compact by just making this epsilon 0 L over 2 times kappa 1 plus kappa 2. Now I believe we're asked to do what is the ratio of the final capacitance to the initial? This is the final right here. So we're asked what is CP divided by CS? So ratio of final to initial. So I'm going to go ahead and get rid of our pictures here. We will make another picture in a moment. Okay. So we have epsilon 0 L over 2 kappa 1 plus kappa 2 divided by 2 kappa 1 kappa 2 epsilon 0 L over kappa 1 plus kappa 2. Well, over just means if I were to put that down here, it'd be the same as multiplying by the top. So we have a kappa 1 plus kappa 2, so that's just kappa 1 plus kappa 2 squared. And this equals the ratio of C parallel to CS. Done. Okay? Well, we could simplify. But we're done. Okay? So that's what we're asked for, except now we're asked, if kappa 1 and kappa 2 are each equal to 1, does the result make sense? Well, kappa 1, kappa 2, each equal to 1. Let's just go ahead and I think we can do this pretty quickly. Kappa 1 plus kappa 2, this kappa 1 plus kappa 2 is 2. Kappa 1, kappa 2 is just 1. So what do we have here? We have, and I said we could simplify and I didn't yet, but now I will. What do we really have? This epsilon 0 L cancels epsilon 0 L. The 2 becomes a 1/4. And so what we really have is kappa 1 plus kappa 2 squared over kappa 4 kappa 1 kappa 2. And this is equal to 1. This is equal to 2. 2 squared. So 2 squared over 4. 2 squared over 4. Sorry, you probably can't see that. 2 squared over 4 is equal to 1. And so, what does this say? It says that if kappa 1 and kappa 2 are equal to 1, then the ratio of the parallel capacitance to the series capacitance is that they are equal to one another. Well, what does it mean if kappa 1 and kappa 2 are equal to 1? What is the dielectric constant of 1? What has a dielectric constant of 1? Vacuum, or air, close enough. They're both the same. So, for these purposes, they're both the same. So, let's look at what that means. What did we have to start with? We had a block that was L by L, an L by L square separated by a distance of L. So we had an L by L square separated by a distance of L that happened to have some dielectric in here. Then we took this dielectric and we turned it another way. Did the L by L by L shape change? No, there's no change in that volume. So what did we have in both cases? If we have kappa equal kappa 1 equal kappa 2 equal 1, what we're saying is this is filled with air. If it's filled with air, what is the difference between the air turned this way or the air turned that way? There's no difference at all, which is why it makes sense that this ratio would equal 1 if kappa 1 and kappa 2 equal 1. Okay, that's it.